So when kids get to high school algebra, they learn all about the distributive property.
For example, they learn that A times B plus C equals AB plus AC.
Then they're introduced to exponents, where we always encounter a problem called the
The
freshman's
freshman's
dream.
dream.
Now, this is when students try to distribute an exponent to an entire expression. For example, they think that a plus b squared equals a squared plus b squared when a does not equal 0 and b does not equal 0. Well, guess what? We're here to crush all the freshmen's dreams everywhere.
Now, the A does not equal 0 and B does not equal 0 part is important because this equation will work when either A or B equals 0. That's because A plus 0 squared equals A squared plus 0 squared. But that's boring and really quite obvious, so we restrict A and B and don't let either of them equal 0.
We'll first look at a simple numerical counterexample. So let's let a equal 1 and let b equal 2. And then we'll plug them into our equation. If the freshman's dream works, then this is what we would get. 1 plus 2 squared would equal 1 squared plus 2 squared. And that's going to simplify to 3 squared equals 1 plus 4. And then that will further simplify to 9 equals 5. But clearly, 9 does not equal 5. So this dream doesn't even work for one of the most trivial examples we could think of.
Okay, so we see that it doesn't work in this specific example, but will it ever work? Or is there some way to show that it won't ever work, no matter what numbers we're using?
Well, there actually is a way to show it will never work no matter what numbers we use for a and b. It's a bit more abstract, but we'll use geometry to help us understand what exactly is going on.
First, we have a square where each side has a length of a plus b. Since the area of a square is the length of one side squared, the area of our square is a plus b squared.
Now we'll go ahead and mark off where a and b are on our square. Now since this length is a, this length is also a. Likewise, since this is b, that length is b. And the same goes for the other direction. That's a, so that's a, this is b, so this is b.
From looking at the picture, you can see that the total area of the big square equals the sum of the areas of the rectangular pieces we broke it up into. So let's look at the area of each cutout. So this one is a times a, which equals a squared. This one is a times b, which equals ab. Same for the other side. This one's AB, so the area is AB. And last, the little cutout is b times b, which equals b squared.
So as you can see, the area of our square is a equals a plus b squared, which also equals a squared plus b squared plus ab, which simplifies to a squared plus b squared plus 2ab.
Now you can see that a plus b squared can't just equal a squared plus b squared because we have an extra 2ab left over. So we have shown that a plus b squared equals a squared plus b squared plus 2ab, which disproves the freshman's dream that a plus b squared equals only a squared plus b squared.